Good morning, everyone. I'm Jayani from Monash University, Australia, and my talk title is Generating International High-Dimensional Data Structures. And this is a joint work with Professor Dai, Dr. Paul, Dr. Michael, and Dr. Tianga. Imagine you've recently developed a clustering algorithm, and you need to test that algorithm with a data structure. Let's assume you generated a data with a spherical blob with a sample size with a small or a large. Likewise, then you know that this algorithm works well because you already know the data structure looks like. It's so polite. But the problem is not like that. The data structures can be so complex and your algorithms can be work and can't be work as well. The question is that the real world data sets, like in genomics, in censoring data, in forensic data, there are so many complex structures over there. And also, there are some existing softwares like Splatter, GeoZoo, SNE Data, and ML Blanch. What are a characteristic of these data structures are the Splatter's data look like more biological data, and the GeoZoo more contain the data structures that can be used to test t-SNE and the UMAP, like nonlinear dimension reduction technique. And also, the SNE data also contains some benchmark data sets, and the ML Blanch also useful for check most of the machine learning algorithms. But the problem is that the control over the clustering data structure, because if you are setting up a benchmark algorithm, there should be a possibility or there should be a facilitated how the clustering data look like. That's why our package cardinalR comes on. The cardinalR comes from one of the bird in cardinal, and since it is in the R package, we are named it as a cardinalR. It's abbreviated as collection of various high dimensional data structures in R. What we are doing in here is that we are generating different kind of data structures in arbitrary dimensions. And also, we can control over background noises, dimensions, and noise dimensions as well. And another advantage of using our package is that we know the true data structure looks like, because all the functionalities, all the mathematical functions are described over there. This is the first glance that I used to make the package, because if you are making the package, you have to think about the design of the package as well. Since I had so many data structures in my mind, first of all, I thought to draw those of things and making how that groups can be worked. That is the way that this sketch comes on. My package mainly contain two types of generators. The first thing is that the shape generators. Mainly it contains 13 shape generators that you can use. As you can see over here, we can see branching, linear, pyramid, Swiss roll, cone, Mobius, S-curve, trefoil, cube, polynomial, sphere, and trigonometric. All of these are visualized using the software called Langiver. As you can see over here, we can talk about extension version of each of these one later. As you can see over here, each of the data structure look like with a different densities, different number of points, different number of dimensions as well. And also, another important thing is that each of these data, the shape generator contain two parameters. The first thing is that number of points. The second thing is that number of dimensions, because we can generate each of these shape generators in arbitrary dimensions. This is the first example with the branching. What is the purpose of using branching data? Which is that branching data is more useful when you are dealing with the nonlinear dimension reduction algorithm. I don't know you heard about, there is an algorithm called FATE, which is actually testing the branching data structures are working well or not with the nonlinear dimension reduction layout. That is why I wanted to generate this data structure over here. As you can see, this all contain the two parameters, n, which means the number of points, and p, where is the number of dimensions as well. And also, this will be interesting to change the number of branches as well, because we can check whether if the data structure contain 2 branches, is it going to work well? 3 branches, is it going to work well or not as well? This is like a comparison. For each of these branching data structures, the data structures can be generated where the branching is originated in a specific point, and maybe with the different shapes, can be linear or can be nonlinear as well. Another shape that I wanted to add into my package is a pyramid shape. What is the interesting point over here is that, as you can see in here, each of these pyramid has different densities, right? In the tip over here on the pyramid has a different number of points than the other corner. It is also interesting when you are dealing with different type of clustering and the nonlinear dimension reduction methods as well, because some of the dimension reduction methods working well if the density is low within the structure, and some of the dimension reduction methods are working bad when the density is high. That is why I generated these data structures to check that how these are working. Another interesting thing is that the cubes, because in the real world you can see different types of cubes over here. This is like a more grid shape, and this is like a more randomly points are generated in a cube, and this is where the cube with a hole. Why the cube with a hole is interesting? Then because I am working mainly on the dimension reduction data, and that's why I wanted to focus more on the dimension reductions. Because if you can see over here with these data structures, when you are putting this into a 2D paper, it can be separated into 4 clusters because it has a hole in the middle. Another interesting thing is that this a polynomial data. This can be a quadratic or a cubic as well. These all are, for example, I generated all of these structures in 4D, but you can make this in arbitrary dimensions as well by adding noise dimension to the exact data structure. Another interesting feature is that a sphere. You can see in the real world, you can see different type of spheres as well. As you can see over here, this is just a line with a really small density in the sphere, and this is just the random points over all the dimension. And also this is another interesting data structure that I found, which is that when we have a huge spherical ball, there can be 3 small spherical balls within that structure. That is also interesting because sometime when you apply this to a PCA or another dimension reduction algorithm, it can be separated these 3 globes inside into a separate dimensions as well. This is with the trigonometric. This is interesting when we have a different nonlinear patterns in the data structure, because sometimes when you are testing different type of algorithm, the complexity of the structure is important in the different dimensions. That's why I came with the idea to generate the different trigonometric structures in the arbitrary dimensions. Then let's see what can be implemented. For an example, I took 3 data structures from my package with 3 shape generators. The first one is as you can see over here, this is a pyramid shape, but the base is like a star. That is the first data structure that I chose. As you can see over here, if I put this one into 2 dimension, I started thinking about it's like a star in the base. Then I added a small density in the next dimension, like a really small density. Since I want to have it as like a pyramid, I add another random noise to the other dimensions as well, which make that as a pyramid, but it has a shape with a star at the top, at the bottom. That is the first data structure I have chosen. The second one is this one. It's like a more nonlinear pattern. How I generated that one? First, I think that it's like a sphere. Then I added a small noise to make it as in the other dimension. Then I wanted to make it as more nonlinear because I want to check the nonlinear pattern. That's why I make it as a more nonlinear over here. That's why it's when it goes to the hovering over in the animation, it's look like a cyclical pattern. The next data structure is that the hemisphere. It's like a half of a sphere. How do I think about that part is that first I think it as like a half of a sphere. Then I add another noise dimensions to that one. Since I want to make it as how this can be make it as a more cyclical, because these are like all with a nonlinear pattern, I make it a cyclical in the fourth dimension. Let's combine this all together. I have another function in my package called gen multiclusters. If we pass, because I already have different type of shape generators, I can pass all these shape generators to my gen multicluster function, and I can assign how many number of points should be within each cluster. And also I can make how many number of dimensions can be allocated and how many number of clusters. And also I can specify the location of the clusters as well. It's like a centroid of the clusters are mentioning. And also scaling is important. What is the importance of using scale is that when we are making the clusters, some of the structures can be small than the other structure. That's why I want to make this with the scaling as well. That's why I have the parameter scaling. The shape actually contain all the shape generators that I can pass within the multicluster function. And the rotation also important, because if you take in a one structure in like a x1 and x2, maybe the first two dimension, the other structure can be rotated into other direction as well. We can specify that one using this package, through this package as well. And also another interesting thing with the clustering is that adding the background noise, because background noise can make different algorithm check the performance with the different parameters as well. That's why I wanted to do that. And in here, this is the example that I used earlier with the pyramid shape cluster and the cyclical cluster over here and the hemisphere. And also I added small like a random noise to the data structure as well. And also my package contain already some of the already generated data structures. This is like two of them. As you can see in here, the table shape is really important because you can extract whatever you need. All the dimensions are specified over here, and all the cluster look at it as a cluster label. This is with the Mobius with the Gaussian cluster. The Mobius shape is also important because it contains like a cyclical pattern again, but in the middle we have a globe. And in here, this is another data structure that you can generate. It's with the like a different number and different types of the Gaussian clusters, but you can change the number of points of the Gaussian cluster, and also you can change the density of the clusters as well. This is the application that I've chosen to explain how this is working. This is with the like a five data structures over here. And as you can see, the shapes are really different, and the positions also I mentioned with the like a it's like a more separated to each other. If you do that and apply any kind of the dimension reduction method, this is with the like a 6-dimension reduction method that I have chosen. This is with TSNE UMAP, FATE, TriMap, and PacMap. And also this is with the PCA. Can you see the difference? Some of the ones are like too separated the data structures as they don't want to, but still the PCA try to preserve the data structure much as they can. And finally, you can use my package cardinalR to generate different shapes data structures within the arbitrary dimension with the different number of points as well, and with the different locations. And also you can add background noise, noise dimension to the data structure as well. And if you want to and build better algorithms by knowing what your data really look like. And if you want more information, please scan our QR code. Thank you so much.